So having looked at the background of what the transition metals are like, or their key characteristics, we now get onto the question of, well, what do they actually do chemistry-wise? The short answer to that is not much. They don't do many reactions, they're quite unreactive, and all of their chemistry is kind of dominated by one key characteristic. What the transition metals are famous for being able to do is form what we call complexes. Now, complexes aren't really something you've looked at in any other topic in chemistry so far, so this is going to look a wee bit different. But I promise you it's not too difficult, it just looks a wee bit new to you. So let's look at what complexes are, how they form, and then a little bit about the definitions of them, a little bit of how we can predict what they're going to be. So a complex ion is an ion comprising one or more ligands attached to a central metal cation by coordinate bonds. So it's a one-line definition, but there's obviously an awful lot going on there. So if I try and build it up in stages, let's look at a transition metal, because I said that transition metals often form complexes. If I look at iron as an example, let's go for iron 2+. Iron 2+ has a positive charge, it's therefore electron deficient. Therefore, it would be quite happy with the scenario where something with electrons, or a surplus of electrons, can give electrons to it because it's got a positive charge. So let's think about how it could accept electrons, and what we can go back to is our definition of what we actually mean by a transition metal. A transition metal is an element which forms at least one stable ion with a partially filled d subshell. That's true about iron 2+. When you have the electron configuration of iron 2+, you will find it's not got a full d subshell. There's an emptiness to the subshell. In other words, there's space for electrons to fit in, space for electrons to be donated to it. If you think about what those d orbitals are like, here's a little diagram. Again, don't need to know this, but this is what d orbitals look like. They're lots of interesting shapes, but they point in lots of different directions. So if we think about putting all those facts together, we've got iron here, iron 2+. It's electron deficient. It would be quite happy to accept some electrons. It's got emptiness to its d subshell, so empty d orbitals, which can accept electrons, and those d orbitals point in a variety of directions, so it's basically surrounded by empty orbitals. That means it's actually quite well set up to form coordinate bonds. So if you remember what a coordinate bond is back from AS level, it's basically like a covalent bond, but don't worry about being covalent. It's a bond where you have both pairs of electrons, or both of the electron pair coming from the same atom. Basically, if we think of an example like water, it comes about when you got things with lone pairs. Lone pairs can be donated into empty orbitals and donate both pairs of electrons, both electrons of a pair into the empty orbital. So what happens with iron 2+ is we actually do find lone pairs get donated into transition metal ions, and often quite a lot. Iron can actually take up to 6 coordinate bonds pointing towards itself. So you might remember from AS, we sometimes show coordinate bonds with arrows showing the direction of donation. So if I took 6 water molecules, now only one of these lone pairs will actually donate, we'll get back to that later, but the lone pairs can actually donate into the iron 2+ and form 6 coordinate bonds. That's what we mean by a transition metal complex. If we bring back our definition again, a complex ion is an ion comprising of one or more ligands. A ligand is just something that forms a coordinate bond to a transition metal ion. One or more ligands attached to a central metal cation by coordinate bonds. So we've got all those key ingredients in this picture I've got here. A metal ion in the middle. We've got coordinate bonds from what we call ligands, which are things which donate coordinate bonds to transition metal ions. Now this overall thing is quite big and it's got an overall charge. The charge comes from the combination of the metal ion and the ligands. In this particular case, the ligands, which are the water molecules, are neutral, so the only charged thing is that iron 2+, which gives it a 2+ charge. That's your first insight to what a transition metal complex actually looks like. Now sometimes you will be asked to draw out these complexes, but often that's a wee bit cumbersome, so we've got a little shorthand version of how you write them, which is explained here. Complex is written as M, transition metal, ligand in brackets with a wee x, the number of ligands beside it, with the charge to the top right of the square brackets. So there's a lot going on there. Bringing it down, if you see square brackets, it means it's a complex. The first thing you put inside the brackets is whatever the metal ion is. Then in round brackets beside that metal ion, you'll put the ligand in, and then the number of those ligands to the right of it, little subscript there. The overall charge of the whole thing, including the ligands and the metal, goes in the top right of the square brackets. Obviously, it's much easier looking at some examples. So the example I just drew out for you had an iron 2+ ion, 6 waters. This is how you draw it shorthand. Fe H2O 6 times, the overall charge of the ligands and the ions is 2+. Other examples, a cobalt with 4 chlorides attached to it. So that's CO2 plus 4 Cl minuses gives you 2- charge. You can have a mix of different ligands. You could have 4 NH3s in this copper and 2 waters. You just list them after each other. NH3 4 times, H2O 2 times, then the overall charge outside the square brackets. That bit about the charges is emphasised again here. Note that the formula of the ion is always written inside the square brackets with the overall charge written outside the brackets. So we don't put the charge in the metal ion, we just put the overall charge at the end. So having looked at the basics of what a complex is, let's hone in a wee bit more in terms of what ligands can attach to form complexes to metal ions. We've got a little definition here to start with. A ligand is a species. It can be a molecule or an ion. It can be neutral or negatively charged, in other words, that can use its lone pair of electrons to form a coordinate bond with a central metal atom or ion in a complex. So I'm going to look through essentially what the content is in the rest of this paragraph. I'm not going to read through it because I think it won't go so well on the video. I'm going to do a wee bit of drawing for you here, so you can make note of this if you want. So we're going to try to categorise some of the ligands you might come across within the transition metal complex kind of field. First category would be your neutral ligands, which we've already looked at an example of. So neutral ligands, there can be 3 main examples, but obviously more could come up. Water is a key example. It's got 2 lone pairs. Now, in reality, it's only ever going to really use 1 lone pair in forming a complex, because if you remember back to shapes, those 2 lone pairs are actually pointing in quite different directions. They're about 109 degrees apart from each other. So there's actually only one of them will form a coordinate bond, but you've got the scope there to form at least one. Within a complex, you would know water as aqua. It's got kind of different terminology. So in other words, if I had the complex iron with 6 waters attached to it, a way of kind of expressing that complex in a kind of shorthand way, we would call that hexa aqua, 6 waters, Fe2+, which gives you the same information as the formula does. Another example of a neutral ligand would be ammonia, NH3, because again, if you think about it, it's got that lone pair that can donate into a metal ion. If we were to give it like a shorthand name, we'd call it amine, not amine. It's got 2 M's like ammonia. So you have hexaamine iron, there'd be 6 ammonias attached to your central ion. The final one seems vastly different. 1,2 diamino ethane. Shorthand form of this sounds a bit confusing. You sometimes compress this to En. It's like the little conventional shorthand for it. Drawing that out structure wise, you've got 2 carbons for your ethane bit, and you got 2 amine groups at the end. So it's an organic molecule. What we notice here is it's got 2 lone pairs on the 2 nitrogens. Why this one is brought up, even though it seems drastically different from those simple molecules, is it's an interesting example of one which has got 2 lone pairs on different ends of a molecule. So as we'll see later, it can actually join to a complex in quite an interesting, different way. So all of these neutral ligands have a lone pair, but they've got no charge overall. However, you can obviously get ligands which do have a charge and have to be a negative charge to have an excess of electrons. So you have some anion ligands. Key examples of it would be your chloride ion. You would call it chloro within a compound, for example, like hexachloro or tetrachloro if you got 4 of them. You've got your cyanide ion, which becomes cyano within a complex. This one is a little bit new to you, SCN. It's known as a thiocyanate ion, but in the context of complex chemistry, we would call it thiocyano. And then everyone's favourite molecule, EDTA, with a 4- charge. Very short name, but a horrifically big structure to it. EDTA, you remember you came across in medicinal chemistry. It's used to sequester metal ions. It stands for ethylene diamine tetraacetic acid, which has this structure here. So you've got the ethylene in the middle. two amine groups on either end, and each of those amine groups are attached to ethanoic acid, which has an old name of acetic acid. So again, what all these complexes have in common is that they have still got lone pairs. So all of these negative charges are lone pairs, and some of them have more than one lone pair and more than one negative charge. EDTA actually has got quite a few lone pairs it could form a complex with. So bearing in mind the fact that we have in some transition metal complexes have neutral ligands and some of them we have negatively charged ligands, we sometimes have to be a wee bit careful in how we express the charges on the overall complex. So what I mean by that is this. If I take this innocent looking formula here, looks a bit strange because it's got a negative charge even though we've got a transition metal positive ion in here. If we think about what's contained within this formula, we've got one Cu ion, and I just happen to know that Cu always has a 2+ charge in a stable ion. It's got 4 chlorines in it, but not chlorine the element, chloride ions. And if I do a wee sum now, we've got 1 2+ charge, we've got 4- charges, 2 + 4- overall gives me a 2- charge. That's why that's the charge on the brackets on this complex. However, with a neutral ligand, if I think of nickel with 6 ammonias in it, attached to it, it ends up with a 2+ charge. The reason that is, it's got 1 nickel 2+ ion. It's got 6 ammonias, but the ammonias have no charge, they're neutral ligands. So the overall charge of the complex just comes from the positively charged metal ion, giving it a 2+ charge overall. One slightly more complicated example, if I look at nickel bonded to EDTA, as we'll look at later, it actually only needs 1 EDTA to fully form a complex. Again, nickel has a 2+ charge, EDTA has got a 4- charge from 4 ethanoic acids. That gives overall a 2- charge, 2 + 4- 2- overall. So we've looked at one way you can categorize ligands in 2 different groups. They can be neutral with just a lone pair or negatively charged with a lone pair. There's one other type of categorization you can give to ligands and how they attach themselves with coordinate bonds to metal ions, and it's the number of coordinate bonds they can form. So this next categorization is known as how dentate they are, which sounds quite strange. The first type is the monodentate ligands. Now breaking down that word monodentate, mono means one. Dentate comes from the idea of teeth, like your dentures. It means one tooth ligand. A one tooth ligand, a monodentate ligand, can form one bond or can bite 1 times to a metal ion. So the proper definition of that is a monodentate ligand has 1 pair of electrons forming 1 coordinate bond to a metal ion. Now, most ligands you look at will be monodentate. For example, your H2O has got forms with 1 lone pair of electrons, ammonia as well. Even the negatively charged ones still only form a bond with 1 lone pair. So chloride ions, your cyanide ions, your thiocyanate ions as well. So give an example of that. If I have nickel with 6 ammonias attached to it, I form 6 coordinate bonds, but importantly, each one of those ammonias is only forming 1 interaction with the nickel. One thing though, I'm being a bit careful there how I draw it. Always trying to show that the nitrogen part of it's forming the interaction, so I wouldn't put the H's in this side because make it look like they're forming the interactions. The N's always on the arrow here. Square brackets shows a complex and it's got 2+ charge because those are neutral ligands. So if you can have examples where you've got 1 pair of electrons forming 1 coordinate bond, clearly you could have more than that. Bidentate ligands as you maybe are able to guess, bi means 2. They've got 2 pairs of electrons forming 2 separate coordinate bonds. So a key example of that would be this ice-range neutral ligand we looked at earlier, 1,2 diaminoethane, to remind you what it looked like here. It's 2 carbons with a nitrogen on each end. And you've got a lone pair on each nitrogen. So 2 pairs of electrons could form 2 coordinate bonds. You're generally only going to get bidentate ligands when you've got a long molecule which has got lone pair, an atom with a lone pair on each side of the molecule. Now you could be asked to draw that within a complex. It's obviously a bit more complicated because it's a long molecule. Often skeletal formulas will help us with this. So if I do the skeletal formula for this structure, 2 carbons in the middle. So you can have examples with that structure. So for example, if I look at chromium with 3 of these, we call it EN ligands attached to it. Again, don't worry how I know it's 3, we'll get to that later. So it's going to have 6 interactions because you get 3 ENs giving 2 each, gives you 6. So we start with the NH2, forming the coordinate bond with this lone pair. Then we just need to link them up because remember, sets of 2 come from the same molecule joined by carbons. So I could draw it like this. So if you look at that, again, that's a nitrogen, carbon, carbon, nitrogen. That's 1 EN. Nitrogen, carbon, carbon, nitrogen, another one. Nitrogen, carbon, carbon, nitrogen, another one. So that's a complex formed from bidentate ligands, chromium 3 plus ion in the middle. So it's 2 pairs of electrons forming 2 coordinate bonds to the same metal ion. You can, obviously in general, if you got 1, you got 2, you can't go higher than that. We kind of go a bit more general once we get beyond that. We call them polydentate ligands. So poly means many. So polydentate ligands means more than 2 pairs of electrons, giving more than 2 coordinate bonds, and not write the whole thing. One specific example of a polydentate ligand you might come across is the Hexadentate Ligand, which obviously, again, I'll not write out the full definition, but means means 6 pairs of electrons forming 6 coordinate bonds. Why I say you might come across that is because we've looked at one of those already. EDTA 4- is a hexadentate ligand. If I draw it out again in skeletal form, again, if you do a bit of analysis with some lone pairs, it actually can form 6 interactions with lone pairs quite easily. You've got a lone pair on this negatively charged oxygen, and here, and here, and here. You've also got lone pairs on these nitrogens. That gives you 6 potential places you can form an interaction with a metal ion, which gives you 6 potential coordinate bonds being formed. Now in this particular case, I think it would be a bit mean to get you to draw it out, but you can see an example in your notes on the right hand side here on page 3. This is a copper ion attached to EDTA. Again, it looks like a lot of bonds, a lot of molecules here. It is actually one EDTA molecule, and you can pick out 2 nitrogens forming coordinate bonds to the copper and 4 oxygens forming the coordinate bond to the copper. And if you follow the bonding round, you will actually see that they're all part of the same EDTA molecule. So to summarise that section, because there's a lot of new stuff there, what we've introduced is the idea of complexes. Complexes are things formed from transition metal ions when things with lone pairs bond to them with coordinate bonds, because transition metal ions are electron deficient and would quite like to receive some electron density. They receive electrons into their empty d orbitals, which is your definition of a transition metal. The things which bond to the metal ions are called ligands. Ligands have got lone pairs. They can be ions or neutral molecules, but have the lone pairs. We've looked at some examples of neutral and charged ligands, depending on their bonding. And we looked at some examples which only form 1 coordinate bond or many coordinate bonds to that metal ion, giving you different complexes.